So what we're going to be talking about today is some rules for exponents. These are just some basic rules that will apply a lot as you progress through the world of algebra. So the first one deals with multiplication. So it looks at, for example, if I wanted to take 6 to the third power and I wanted to multiply times 6 to the fifth power. Or if I had a variable, n to the eighth times n to the fourth. Something like that. Okay, so let's take the situation on the left. Okay, and let's think about what do exponents really mean. Well, 6 to the third power really means 6 times 6 times 6. 6 to the fifth power means 6 times 6 times 6 times 6 times 6. So I'm just multiplying those two sets of things together, right? And if I look at it, that just means I have 1, 2, 3, 4, 5, 6, 7, 8 sixes that I'm being multiplied together, and the shortcut for that is 6 to the eighth power. Okay, over here, n to the eighth power. N times n times n times n times n times n. You can see why we have exponents. And then times n to the fourth. 1, 2, 3, 4. Right? So if I look at that, well, I end up with a total of 12 n's there, so that's just n to the 12th power. Okay? Now, if we think about the pattern that we're seeing there, right, what do I do with 3 and 5 to get 8? What do I do with 8 and 4 to get 12? Well, I simply add them. So we can see that our pattern is when we have a number with an exponent, and we are multiplying that same base number with a different exponent, right? We can see our rule is we add those exponents. Okay, we don't multiply them, we add them, right? In our example, 6 to the third times 6 to the fifth is 6 to the eighth. 3 plus 5 is 8. Right? N to the eighth times n to the fourth is n to the 8 plus 4 power n to the 12th power. So when we multiply exponents, we want to add those exponents together. Again, the bases have to be the same. I can't do 6 to the third times 4 to the fifth and add my exponents because we can't combine those things together. They're different bases. But when the bases are the same, we want to add those exponents. Now, division is going to be similar. Okay, let's say I had n to the fifth power divided by n squared. Okay, I'm going to write it as a fraction there for my division. Well, if we think about what that means, right, n to the fifth, there's your 5 n's. N to the second is 2 n's, right? And then we can cancel out. I know that, for example, on this one, that I can cancel out, right, 2 n's and 2 n's. So I can get rid of those. Okay. Cancel those out. So what's that leave me with? Well, that leaves me with n to the third power. Okay, let's look at one more example. 6 to the fourth divided by 6 to the third. Well, that's 6 times 6 times 6 times 6 over 6 times 6 times 6, right? And again, we can cancel out 3 6's from both the top and the bottom and just be left with 6 to the first power, or more simply, just 6. Okay, so as we examine our pattern here, what do I do with 5 and 2 to get 3? What do I do with 4 and 3 to get 1? I simply subtract. Okay, so a to the x power divided by a to the y power is simply a to the x minus y power. We want to subtract our exponents when we are dividing. Okay. Now, there's some other patterns that happen with exponents, okay? Let's take, for example, when we have a base of 10, okay? 10 to the third power. That's 10 times 10 times 10. That's 1,000, right? 10 to the second power. 10 times 10 is 100. 10 to the first power, right? Just 10. Now, we start looking at the pattern, right? What's happening as we decrease? Well, we're dividing by 10. Some of you might know, well, we're just getting rid of a 0 or we're moving our decimal place over a spot. Okay, which is all true. So logically, right, what would be my next exponent? 10 to the third, 10 to the second, 10 to the first. Well, that would be 10 to the 0. I'm decreasing by 1 each time. If I follow my pattern on the right side and I get rid of a 0 or divide by 10, okay, I'd see that 10 to the 0 power is 1. Okay, so sometimes in math we have things that maybe logically don't make sense, but we need them in order to continue on a pattern, right? There's doesn't mean 0 tens, right? 0 tens is 0, right? There's nothing there. Okay, it just simply follows the logical pattern that we establish with exponents. So 10 to the 0 power is 1. Anything to the 0 power is going to be 1, with the exception of 0 to the 0 power, because it doesn't fit into that pattern. Okay, so anything to the 0 power is going to be 1. Okay, our only exception is 0 to the 0 power. Okay, so that's our third rule. Okay, now if we continue this pattern on, right, what would be my next logical exponent? 3, 2, 1, 0. Well, it would be -1, right? And then -2, -3. If I continue my pattern on the right, okay, again, each one is a tenth of the one before. Okay, 0.1, or more simply, 1 over 10. Okay, 10 to the -2nd would be 100th. 10 to the -3rd would be 1,000th. Okay, now we start to see some relationships there, right? 10 to the 3rd is 1,000. 10 to the -3rd is 1,000th. 10 squared is 100. 10 to the -2nd is 100th. Okay, so our pattern for this is, right, if I have a number and it has a negative exponent, okay, we can write that as 1 over that number with the positive exponent, right? So 10 to the -2nd, for example, okay, equals 1 over 100. Well, 100 is 10 to the positive second power. Okay, so we're just putting that positive form of that exponent and then putting in the denominator, right? If I have 3 to the -4th power, well, that's the same as 1 over 3 to the positive 4th power. If I have 12 to the -5th power, that's the same as 1 over 12 to the positive 5th power. Right? So we're just making the exponent positive, putting in the denominator, with 1 being our numerator. And again, we can logically follow the pattern there and see why it works. There's nothing dealing with negatives. We don't make 12 negative or do anything like that. It's just, again, negative exponents help us to follow a pattern that's been established with our positive exponents to carry that out. Okay, so quick recap here, okay, of our 4 exponent rules. So when I have multiplying exponents, right, my rule is that I add those exponents. 3 to the 4th times 3 to the 3rd is 3 to the 4 plus 3 power, which is 3 to the 7th. When I divide exponents, okay, my rule is I subtract. So that's 3 to the 5 minus 2, or more simply 3 to the 3rd power. Okay, anything to the 0 power is always going to be equal to 1, with our one exception being 0 to the 0 power. And a negative exponent, like 3 to the -3rd, we simply put 1 as our numerator, and then our denominator becomes, in this case, 3 to the positive 3rd. We use the positive form of the exponent there, with 1 being our numerator.